Welcome back, grade 10s. In today's lesson, we are going to complete transverse pulses and waves. We are going to go over some past paper questions. So we're going to complete these examples in order to just make sure that we can understand and apply what we've learned. It's very important that we realize that when it comes to wave questions, we have 4 formulas to play around with. Now, based on the information that we're given in a question, we need to figure out our known variables and our unknown variable. And we then come back to these formulas over here and we figure out which formula to use based on the information that we've been given and what we're trying to figure out. So let's get going with our third lesson of transverse pulses and waves. Let's take a look at the first example. A wave is traveling along a rope that is 15 meters long. 10 full wave cycles fit along this 15-meter rope, and the wave travels at 9 meters per second. So we've been given the speed of the wave. We were also given some information about the length of the wave and how many wave cycles fit into it. The first question is, what is the wavelength of the wave? To figure out wavelength, we need to be given speed and frequency, or speed and period. But in this case, we've only been given speed. However, we were given enough information here to work out the wavelength based on logic. This diagram here represents 10 full wave cycles over the 15-meter length of rope. So that tells us that 15 meters fits 10 wavelengths. But we've got to figure out the distance of one wavelength. 10 divided by 10 is 1, so that would give us one wavelength. 15 divided by 10 is 1.5 meters. So that tells us that each wavelength over here is 1.5 meters. And if we add up all these 1.5 meters, all 10 of them, we'll get the total of 15 meters. So in this case, we couldn't apply a formula. We had to use some logic. So to calculate the wavelength of the wave, we say 15 divided by 10. We don't have to say 15 meters divided by 10 cycles. 15 divided by 10 will do, and that gives us one wavelength of 1.5 meters. So now we have the speed of the wave and we have the wavelength of the wave. And the next question asks us to calculate the frequency of the wave. So going back to our formulas, well, again, we were given the speed and we've calculated the wavelength and we need to calculate the frequency. So which formula below includes all 3 of those variables? And it is this one over here. Now this formula is given to you on a formula sheet. Speed is equal to wavelength times frequency. You don't have to rearrange the formula. You may just start plugging in numbers. So you can put 9 in place of speed and 1.5 in place of wavelength. Or alternatively, you may rearrange the formula to say that frequency is speed divided by wavelength. Either way, you will derive the same answer. I rearranged my formula up front. So the frequency of the wave is the speed divided by the wavelength, which is 9 divided by 1.5, and we get a final answer of 6 hertz because frequency is measured in hertz. If the frequency of the wave is changed to 3 hertz, what would be the speed of the wave? Now this is a bit of a trick question. Remember that we learned that the speed of the wave depends only on the medium through which the disturbance travels. we have not changed the medium. Therefore, the speed of the wave will remain 9 meters per second because the medium remains the same. Now take a look. The frequency of our wave we calculated to be 6 hertz. And now we are reducing it to 3 hertz, which means that we are halving it. So the next question is, if the frequency of the wave is changed to 3 hertz, what would be the wavelength of the wave? And that brings us to a very important discussion on relationships that are proportional and inversely proportional. And those questions are asked very regularly in lots of different contexts with lots of different types of equations. So I'd like to take you through those relationships now. Let's take a look at this wave speed formula. So wave speed is the wavelength times the frequency of the wave. Now over here, we can see that this is a multiplication. The speed, wavelength, and frequency are along the same line. There's no division. There's no denominator. I am going to put a multiplication sign over here, just for clarity. Now, if my wavelength remains constant and I increase my frequency, what will happen to the speed of the wave? So let's say that the wavelength remains constant at a value of 2. If my frequency is 1, then the speed of my wave will be 2 times 1, which is 2. If my frequency is 2, then the speed will be 4. If my frequency is 200, then my speed will be 400. And if I reduce my frequency to 100, then I will reduce my speed to 200. So what this tells me is that the relationship between speed and frequency is directly proportional. As one goes up, the other one goes up. As one goes down, the other one goes down. And they go up or down proportionately relative to each other. Meaning that if I double the one, I double the other. If I halve the one, I halve the other. So if my frequency is doubled from 100 to 200, then my speed will double from 200 to 400. It's not an addition and subtraction, it's ratios. So it is division and multiplication. Now, in the same way, if I rather keep my frequency at a constant value and I change my wavelength, so let's make the frequency a constant value of 4. So if my wavelength is 2, then the speed of my wave will be 8. And if I increase my wavelength to 8, 8 times 4 is 32. So the speed of my wave will be 32. And if I reduce my wavelength to 2, again, then I reduce the speed of my wave back to 8. So again, if frequency doesn't change, if I increase my wavelength, I increase my speed. And if I decrease my wavelength, I decrease my speed. So what we've established from that is that the relationship between speed and wavelength is also directly proportional. So what this tells us is that speed and wavelength are directly proportional. Or we may say that speed is proportional to wavelength. We use this symbol. Saying that wavelength is proportional to speed is exactly the same thing. We may also say that speed and frequency are directly proportional, meaning that the speed is proportional to frequency or frequency is proportional to speed. And this is going to apply to any equation where there's multiplication. So if we have a generic equation of A equals B times C, we can then say that B is proportional to A and C is proportional to A. If we have F equals ma, force is mass times acceleration, which is a formula that we will work with next year when we do Newton's laws, then we can say that force and mass are directly proportional, and we can say that force and acceleration are directly proportional. Now let's go back to this equation where wave speed is wavelength times frequency. In the last lesson, we learned how to rearrange formulas. So now we are going to rearrange that formula as wavelength is wave speed divided by the frequency, and the frequency is the wave speed divided by the wavelength. So both of those are derivations of this original formula, and we've just rearranged it. Now what we can see is that wavelength and speed, they are both still along the numerator. So wavelength and speed are still directly proportional. And we can see that frequency and speed, that are both also along the numerator, are also still directly proportional to each other. The relationship is not going to change when we rearrange the formula, unless we've rearranged it in the wrong way. But if we've done it correctly, the relationship is still maintained. But what I'm very interested in now is looking at the relationship between wavelength and frequency. Now, by putting wavelength on one side of the equation on its own, or putting frequency on one side of the equation on its own, we can work out the relationship to the other variables. So again, wavelength and speed remain directly proportional. Frequency and speed remain directly proportional. But what is now the relationship between wavelength and frequency? Let's give the wave speed a constant value of 10. So if the frequency is 1, 10 divided by 1 is 10, so the wavelength would be 10. But if I increase my frequency to 2, then I have now reduced my wavelength because I'm dividing by a bigger number, so my wavelength is now 5. And if I increase my frequency to 5, then I'm dividing the 10 by a bigger number, so now my wavelength would be 2. If I reduce my frequency to 3, then 10 divided by 3 is going to be 3.33. So I have therefore, by dividing by a smaller number, increased my wavelength. So the relationship between frequency and wavelength is inversely proportional or indirectly proportional, meaning that if this one goes up, then this one goes down, or if this one goes down, then this one goes up. And we're going to see the same relationship here. So frequency is speed divided by wavelength, provided that the speed is constant, and I'm giving it a value of 2. If the wavelength is 1, then the frequency will be 2. But if I increase my wavelength to 2, then I decrease my frequency to 1. And if I decrease my wavelength to a half, then my frequency will go up to 4. And so again, what this means is that the relationship between frequency and wavelength is inversely proportional. Again, no matter how you rearrange that formula, you're not going to change the relationships between the variables. Now, we can see the exact same relationship with our generic equation. If A is B times C, then B is A over C and C is A over B. The relationship between A and B is directly proportional. The relationship between A and C is directly proportional. The relationship between B and A, directly proportional. The relationship between C and A, directly proportional. That hasn't changed when I rearranged my formula. And because of the division, with B being at the top and C being at the bottom, the relationship between B and C, or C and B, is inversely proportional. We can see the same thing with Newton's second law of motion formula, F equals ma. F and m, directly proportional. F and a, directly proportional. We can see that relationship over here when we've rearranged the formula. But now the relationship between mass and acceleration, or acceleration and mass, is inversely proportional. So based on this formula and the way that we've arranged it, we can see that wavelength and frequency are inversely proportional. Now, if we want to show this using symbols, there isn't an inversely proportional symbol. So we would say that wavelength is proportional to 1 over frequency, which is the same as saying that wavelength is inversely proportional to frequency. In the same way, frequency and wavelength are inversely proportional. We can see that from this rearranged formula over here, which then allows us to state that frequency is directly proportional to 1 over wavelength, which means that frequency is inversely proportional to wavelength. So going back to our question, well, we worked out that the frequency of our wave was 6 hertz. Now, the next question is, if the frequency of the wave is changed to 3 hertz, that is, it was halved, what would be the wavelength of the wave? And what we need to understand from this is that wavelength and frequency are inversely proportional. So you can simply redo the calculation. We know that our wave speed is 9, that hasn't changed, but now our frequency has been halved to 3 hertz. So our wavelength, which was originally 1.5 meters, is now 3 meters. You can show this by calculation, but sometimes when you're asked this question, you're asked to explain the answer without showing a calculation, in which case you would need to explain that frequency and wavelength are inversely proportional. So because the frequency was halved, then the wavelength would be doubled. So because the frequency was halved from 6 hertz to 3 hertz, then the wavelength of the wave is doubled from 1.5 meters to 3 meters. But it is key that you understand this relationship. A transverse wave has a frequency of 15 hertz. The horizontal distance from a crest to the nearest trough is measured to be 2.5 centimeters. So we've got the frequency, and we don't quite have the wavelength, but we've got some information here that will allow us to work out the wavelength. Now, the first thing is, because this is in centimeters, you should immediately realize that you need to do a conversion into meters. Now, the distance from crest to crest would be the wavelength. But we were told that the distance from the crest to the nearest trough is 2.5 centimeters. So you need to realize from that 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 represents half a wavelength. Therefore, a full wavelength would be 2.5 centimeters plus 2.5 centimeters, which is 5 centimeters, which needs to be converted into meters. Coming back to our question, the first question is, what is the period of the wave? And we can work out the period of the wave based on the frequency alone. Period is 1 over frequency, which is 1 over 15, and period is time, so it is measured in seconds, and we round off our answers to 2 decimal places. The next question asks us, what is the speed of the wave? So we have the frequency that was given to us, and we can calculate based on the information the wavelength of the wave, and based on frequency and wavelength, we may calculate the speed of the wave. We must show this conversion up front. So you must show 2.5 times 2 is equal to 5 centimeters, and then show your conversion into meters. You may also say, as I've taught you, 5 times 10 to the minus 2 meters. The speed is the wavelength times frequency, which is 0.05, or 5 times 10 to the minus 2 times 15 hertz, which gives us an answer in meters per second. It's 0.75 meters per second. Now, instead of applying this formula, we also had the option of using this formula over here. Because remember, we were given enough information to work out the wavelength, and we were given the frequency of the wave. We calculated the period of the wave. So whether we use this formula or this formula doesn't actually make a difference to work out the speed of the wave. I would still recommend using the 15 hertz, meaning using this formula, because this number over here is rounded off. So if you're going to use this formula, your speed value would be slightly off, just because of the rounding off here. I would also recommend using this formula in case, for some reason, you got this answer wrong. However, marks do carry over. So essentially, it doesn't really make a difference which of these formulas you use. Study the following diagram and label parts A to D. So here's part A. Crest to crest distance represents the wavelength. B is the top of the wave, which is called the crest. C is the distance from equilibrium position to the bottom of the trough, which is the amplitude. And D is the bottom of the wave, which is the trough. The diagram below shows 2 waves, A and B, of the same wavelength but with different amplitudes crossing each other. The amplitude of wave B is half the amplitude of wave A. Going to look at the diagram carefully. Wave A is the solid line, and wave B is the broken line. And we were given the length from the top of the crest to the bottom of the trough of wave A in centimeters, and we were told that wave B has half the amplitude of wave A. So we need to read the question carefully, and we need to look at the diagram carefully. What type of wave is represented by the pattern above? It is a transverse wave. Define the wave type above. This is your definition, word for word, of a transverse wave. It's a series of disturbances where the particles of the medium move perpendicular to the direction of the propagation of the wave. Which circled number points 1 to 4 represent one wavelength? So we've got 1, 2, 3, and 4. And clearly it is 0.2 to 0.4 that represent a wavelength. From the graph, determine the frequency, period, and amplitude of wave A. So not using calculations, but from the graph itself. Now, remember that the frequency of a wave is cycles per second. How many cycles fit in 1 second? Here's our 1 second point. And in 1 second, we got 1 cycle. So the frequency is 1 hertz. The period of the wave is how long does it take for a full cycle? And here we can see that a full cycle takes 1 second. So the period of the wave is also a value of 1, but it's 1 second. The amplitude of wave A, well, we were given double the amplitude of 20 centimeters. So it's going to be 20 divided by 2, which is 10 centimeters. And we always want to convert back to our base unit. We always want to convert back to the meter. So the frequency is 1 hertz because we can see on the graph that in 1 second, 1 cycle fitted in there. The period was 1 second because we could see on the graph that 1 full cycle took 1 second. The amplitude of the wave is 20 divided by 2, which is 10 centimeters, which is 0.1 meters, or 10 times 10 to the minus 2 meters. Draw the shape of the resulting pulse as the two pulses A and B cross and indicate the resulting amplitude. Now, let's recall that the amplitude of wave A is 10 centimeters and the amplitude of wave B is half of 10 centimeters, so it's 5 centimeters. So when these two waves cross each other, then the resulting amplitude is going to be 15 centimeters. To answer that question, you'd need to show a crest and a trough because it is two waves that are actually traveling together. It's not a single pulse. And you'd need to show that the amplitude of each one is 15 centimeters or 15 times 10 to the minus 2 meters. So your marks would come from the correct shape and then from the correct value that you insert here and here. Which pulse property is illustrated in the question above? Now, we know that it is superposition, and we also know that it is specifically constructive interference. And the reason that it is constructive interference is because it's two crests and it's two troughs. It's not crest minus trough, which would be destructive interference. Waves generated by flicking one end of a rope are shown below. The waves are moving to the right such that time taken for 3 consecutive crests to pass a point is 0.4 seconds. Now this over here, 3 consecutive crests, what does that actually mean? 3 consecutive crests, 1, 2, 3, actually means 1, 2 wave cycles. This comes up quite often as a bit of a tricky question. And you need to understand that if you're told that you have 20 consecutive crests, what does that mean? It means 19 cycles. If you have 15 consecutive crests, that means 14 cycles. So 3 consecutive crests actually means 2 cycles. And those 2 cycles take 0.4 seconds. And we were also given this value over here of 6 meters. Now, if we consider that, we have 1 cycle, 2 cycles that fit into the 6 meters. So let's now answer the questions. The first one is determine the amplitude of the wave. Again, what we need to realize here is that this 3 meters over here actually represents double the amplitude. So the amplitude is 3 divided by 2, which is 1.5 meters. Determine the wavelength of the wave. So again, we saw that 2 cycles take up a distance of 6 meters. Therefore, 6 divided by 2 means that one cycle is 3 meters. So the wavelength is 3 meters. Determine the period of the wave. So we now know that 2 full cycles take 0.4 seconds, but the period of a wave is how long does it take for one cycle. So again, 3 consecutive crests means 2 cycles. 0.4 divided by 2 means that one cycle takes 0.2 seconds. Determine the frequency of the wave. Well, now that we have the period of the wave, we can use a calculation to determine the frequency. Frequency is 1 over period, which is 1 over 0.2, which is 5 hertz. Determine the speed of the wave. We've got more than enough information now to determine the speed of the wave because we've got the wavelength and we've got the period, or we can use the wavelength and the frequency. Either way, we are going to get the same answer. I've used the wavelength and the period of the wave. So the wavelength is 3, the period is 0.2, and so the speed of the wave is 15 meters per second. The alternative would have been to say that the wave speed is wavelength times frequency, which is 3 times 5, which is 15 meters per second. And lastly, which 2 points are in phase with point G over here? So in phase requires a full cycle. So it would be G and K. And the other point that's in phase with G is C. So both K and C are points that are in phase with point G. That brings us to the end of transverse waves. In the next lesson, we will start on longitudinal waves.